Welcome everyone back to the Crystal Clear Electronics 2 videos. This is the second video of chapter 20. In this video we continue discussing the software and hardware-based energy saving techniques. Eliud, can you tell us why clock scaling is important to us?
Clock scaling is an important factor because the microcontroller is based on CMOS technology, which has the advantage that in the static state, when the circuit assumes the logic 1 or 0 state, it consumes almost negligible power, but during the state transitions, the power consumption is significant. This method is very flexible as it can be implemented from both external and internal clock sources. The frequency of their output can be reduced by prescalers or multiplied by the PLL. Very briefly, I would like to explain what a PLL is. PLL stands for phase locked loop. It's a hardware unit that can, among other things, provide a clock signal at its output that is a multiple of its input clock signal.
The clock signals can be easily set in CubeMX. Since we write code in the user code sections, the clock network setting can be modified and generated later without any problems. After the system clock multiplexer, we find the sysclk field, which is the main clock source for the processor. This is mapped to the AHB pre-divider, which gives the value of HCLK. The peripheral clock is determined from this through possible fine-tuning using the APB1 and APB2 pre-dividers.
The clock signal can be changed at runtime. Go back to the main.c file and find the init state function inside. This sets the clock frequency according to the selected mode. Click on the Disable PLL function, then press F2 to see the function definition. You can see that it first enables the HSI clock source, then waits until the HSI is active, then sets it as the main clock source, and finally disables PLL. Then, all we have to do is to reinitialize rcc_ask init struct in the change PLL prescaler function with the new parameters we want to set. If we step back into CubeMX and check the section around PLL, then we can see that we are just setting these values from software. When switching the system clock, the value of flash_latency must also be set to the appropriate delay depending on the frequency and the power supply of the microcontroller, which is necessary to ensure that the data read from flash memory is correct. This means that the higher the clock frequency and the lower the supply voltage, the more the system has to delay the CPU execution cycles, thus compensating for the slowness of the flash memory. These values are also shown in this table. For example, at a voltage of 3.3 volts and at a clock speed of 168 MHz, 5 wait cycles are required.
However, care must be taken that the main clock frequency specified for our program is not lower than the minimum frequency requirement of the peripherals used. That can be Ethernet, USB or I2C. Fortunately, CubeMX is there to help and will not let us set an incorrect value if we use the clock configurator.
Computational performance is highly dependent on clock frequency, as instructions are executed periodically. This means that if the frequency is reduced, the power consumption is also reduced, since the CMOS switches change state less often. However, it also slows down the execution of instructions, thus keeping the controller in run mode for longer. Therefore, if you have a computationally demanding task, increasing the clock frequency may actually result in less power consumption to complete the task. For extra acceleration, the ART, or Adaptive Real-Time Memory Accelerator, can be enabled to speed up the task to be completed by the microcontroller. Once the computationally intensive task is completed, you can immediately reduce the clock frequency of the controller, or if you have been using the ART Accelerator, it may be useful to turn it off. This way, there will only be a short spike in power consumption, and then the microcontroller can return to sleep, resulting in only a small increase in average power consumption.
I was thinking of reducing the supply voltage of my system from 5 volts to 3.3 volts. Does this affect the current consumption in any way?
Sure, if you reduce the supply voltage, the current consumption will also reduce. However, attention must be paid to the supply voltage level of the components in the circuit. Of course, it is not possible to use a voltage lower than the minimum required. In general, you can go down to 2.5 volts with almost no problems. For devices that require more power, such as a display, it's worth noting that the internal logic circuitry of the display and the components that actually drive the display may have different minimum power requirements.
My next question will differ from the previous topic. I know that the GPIO peripheral is also CMOS based, so the more often the pin is tipped, the more it consumes. If we use a pin as an output, we are aware of this, but if we don't use the pin, then after reset, they are configured as digital inputs. Can this cause any problem?
Thank you. This is a good question. A sensitive floating pin may start to act as an antenna when exposed to ambient noise. The phenomenon of the pin floating is due to the fact that at this stage, there is no resistor for either supply voltage or ground potential configured in software for the pin within the controller. Believe it or not, this condition can increase power consumption, and it's not easy to detect because the noise changes in both frequency and amplitude. A solution to this is to set these unused pins as analog inputs so that the Schmitt trigger circuit in the peripheral becomes inactive as shown in this figure. In addition, if you do set it as an input, it is also advisable to minimize the speed of the pin, thus reducing the bounce. This technique is well suited for inputs where slow changing signals need to be detected, for example for push buttons. The solutions discussed so far do not really affect the other components of the circuit, since we configured the pins as inputs. However, this is not the case for the additional solution, where the pin is configured as an output, for example in push-pull mode, and then driven to logic 0. In this case, it's important to check the details of the associated circuit to see what effect this step might have.
Thank you for the answer.
You're welcome. And now let's talk a little about event-driven programming. Event-driven means that whenever a result is required to continue a task, you should try to set an interrupt and only wake up the controller when it has an actual task to perform. A good example of such waiting is the case of communications, but it is also a useful technique for a simple LED blinker. With this approach, it is possible to achieve a much more dynamic operation. Generally speaking, if you have more than 3 control states in an application, it is worth using a state machine, which also greatly increases the clarity.
You have heard about state machines in the 7th chapter of Crystal Clear Electronics 2.
Previously, we've talked about the ART Accelerator, but now let's look at what this term actually means. Balázs, can you summarize this, please?
Sure. An ART Accelerator, meaning Adaptive Real-Time Accelerator, is a feature that can load instructions from memory, with the help of the prefetch buffer, more efficiently inside the controller as part of a flash peripheral. When active, it is disabled by default, it prefetches the next instruction, this is the fetch part, and data, eliminating the slow access to flash and thus increasing the number of instructions that can be executed in a unit of time. Optimally, it can achieve up to twice the runtime speedup.
Great, thank you. Now, I will show a diagram to that. Here you can see the process of how the prefetch mechanism works. Instructions are loaded by interleaving. While one flash read is being completed, the next one is already being prepared. The upper part of the figure shows the implementation without prefetch. Of course, when the user is not concerned with computing performance, but with how to minimize power consumption, this functionality can be turned off. This reduces flash usage, which can result in a consumption reduction of up to 10%. Of course, this also largely depends on how much flash memory is used by the program.
The following code snippet shows how to enable or disable this functionality. First, we have to examine whether the accelerator is turned on. If not, we can turn it on by enabling the necessary prefetch buffer, the instruction and data caches. If the cache is already turned on, you can turn it off by disabling the same buffer and caches.
Code optimization can sometimes be a double-edged sword from a debugging point of view, because the compiler might remove important variables during optimization, if you're not careful. This scenario typically occurs with variables used in interrupt routines. For optimization purposes, these are considered unused variables, since during the normal execution of this code, the interrupt handler functions are not called without interruption. To avoid this, we can use the volatile keyword before the variables. This tells the compiler that we have a definite plan for the variable, so let us have it. After this, the optimization for consumption will have an effect in the sense that the compiler will not behave as it does by default, which is the O0, but will start interpreting each code fragment according to the optimization level set. It will no longer generate a one-to-one mirror assembly of C code with the same functionality, but will instead try to optimize its output at the assembly level depending on the type and level of optimization.
The optimization methods are discussed in more detail in Chapter 6, so we will not go into these now.
The STM32F4 family of controllers on the development board includes several peripherals that support direct memory access, or DMA for short. DMA is a data transfer technique that allows data to be exchanged directly between the operational memory and the peripheral without the intervention of the central controller. In this case, the peripherals bypass the controller's CPU and communicate directly with the memory. Thus, until an interrupt is received from the peripheral indicating the end of the data transfer, the controller can be put to sleep. This technique also saves a lot of energy.
At first glance, these may not seem like significant differences. But if you consider that, for example, in a device where several controllers or sensors work together and exchange a huge amount of messages periodically, the difference can be striking.
If you use your device in low power mode, it is advisable to turn off the clock of any peripherals that are not in use, thus reducing power consumption, as some circuitry parts may still consume power even when idle. An example of such a continuously operating peripheral is the ADC. Here, we are showing another code snippet where you can see that, for example, with these program commands, we can turn on and off the clock signal of the GPIO port A.
It is time to talk more about the communication peripherals, more specifically about the optimization of their power consumption. What kind of techniques should we consider?
We have some options, but in general, it is true for serial communications that the most energy can be saved when the bus is in idle state. Another energy-saving option is the DMA, which can write directly to memory by skipping the processor, which is also possible in the previously seen sleep mode, since only the processor core is powered off in that state. You can also try to speed up the communication by increasing the baud rate value. This allows the communication to complete in a shorter time window, so that we can put the controller into sleep mode sooner.
Another option is to reduce the clock frequency of the communication peripheral to the level required by the selected baud rate. This minimizes the unnecessary clock changes in the peripheral.
Another solution can be to compress the data to be transmitted. A good example to illustrate this is if you have a 6-element button row in an application and 2 LEDs whose current states you want to send at the specified intervals. In this case, it makes sense to use a single 8-bit packet instead of 2 separate packets. You may have already heard in previous chapters that if the current peripheral is not currently in use, you can turn its clock off. This is also an it depends situation. If you want less power consumption, then you will get slower communication. This means that the process will take longer, thus reducing the time spent while turned off.
The other end of the story is when you want faster communication, which means higher power consumption. In return, we can keep the peripheral off for longer.
True, but this method is only possible if the power supply is capable of handling this sudden surge in power demand. In I2C communication, for example with an external memory, it is recommended to start addressing, if you have the choice, from the maximum value downwards, not from 0. This trick can achieve quite significant power savings. Let's see how. By default, the open collector output are pulled to logic high with the resistors Rp, so that when communication is initiated, the transistor switches and pulls the SDA and SCL signals to logic low. Consequently, for each binary zero value sent, current flows through resistor Rp, the duration of which depends on the speed of the communication.
Now I understand why you said it's better to start from the maximum value and go down. This method produces the most bits with a value of 1 in the address.
Exactly.
We could fit in this much in one episode. We are saying goodbye for now, but see you in the next video.
Bye!
Bye.